Another type of reaction is an acid-base reaction, also called a neutralization reaction. We've talked about acids a little bit. We've learned how to name them and identify their formulas. Acids are substances that tend to form hydrogen ions in solution. We can recognize them because their formulas begin with hydrogen. If it doesn't begin with H, it's not an acid in Chem 3A. Acids taste sour, and they can dissolve some metals, not all metals. Bases are kind of the opposite of acids. They tend to form hydroxide ions in solution. The ones that we're going to deal with most are metal hydroxides, lithium hydroxide, sodium hydroxide, potassium hydroxide. They taste bitter, which is your body saying, don't eat that, it's not good for you. And they feel slippery because they start to dissolve. They make soap with your oils, and then they would eventually dissolve your skin, so that's not good. So here's some common ones. We've seen all these acids before in learning how to name them. If you look at the names, they all have the word acid in them, so that makes it easy. The bases, metal hydroxides, potassium hydroxide, calcium hydroxide, barium hydroxide. When you look at the formulas, you see a metal and OH. That's what tells you this is a base. So in an acid-base reaction, we have an acid mixing with a base, and they neutralize each other, and the product is water and an ionic compound. Salt is actually a generic word for any soluble ionic compound. So the acid hydrochloric acid reacting with sodium hydroxide forms water and sodium chloride. Acid plus base makes water and salt. So every time I have to say it makes a salt, I think of this picture. This is a salt rifle. Right? Yeah. So the pattern for these reactions is acid plus base yields water plus salt. Remember, not always sodium chloride, some ionic compound. The net ionic equation for many acid-base reactions is going to be the same. Hydrogen ion and hydroxide ion make water. The reason for that is the other ions in the acid and the base form this salt, which is soluble, and so they end up being spectator ions. So let's write molecular and net ionic equations for the reaction between aqueous H2SO4 and aqueous KOH. Which of these is the acid? This one starts with H, right? H2SO4. This is the acid, that's the base. Metal hydroxide is a base. Okay, so what we're going to do here is we're going to write these formulas. So we've got H2SO4, it's aqueous, because they told us that. And we've got KOH, and they told us that that's aqueous. We can predict the products of this in the same way that we did with precipitation reactions. Pull the ions apart, swap partners, put them back together. So H2SO4, we've got the hydrogens, so that's one ion, H plus, and the other one is the SO4, so that's the sulfate. We've got hydrogen ions and sulfate ions. There's two hydrogen ions, but I just want to see the formula for each of the ions. I've got potassium ion and hydroxide ion. In Chem 3A, there are only two ions, one positive, one negative. Don't make more. Then we want to swap partners. So the two on the inside and the two on the outside. Write them down over here. H plus, OH minus, K plus, SO4, 2 minus. So I look at this, and my brain's a little foggy, but I'm looking at this, and I'm like, a positive ion and a negative ion. I just need one of each, and I put them together. And I go, huh? That looks weird, doesn't it? Oh, that's H2O. There's two H's here. It's not H, it's H2O. So let's fix that. H2O. Is H2O? Pardon me?
It doesn't matter if you write from right to left or left to right, no?
You mean in terms of which of these ions goes first?
Yeah.
Okay, so water is kind of a special sort of a thing. Water is not an ionic compound. And yet water does form ions a little bit. So we kind of just, hydrogen's involved, it's going to have some exceptions. So H plus and OH minus, you could write HOH, but then you're going to end up, for mastering chemistry for sure, you're going to end up needing to combine those and write it H2O because it's water.
No, I'm talking about where it's the K first, then the SO.
Oh, you're talking about this one?
Yeah.
You mean, should these be over here?
No, should they be swapped? SO4 before the K, does it matter? No?
The K has to be first.
Okay.
Because the guy always comes first and then the girl. The masculine, feminine, positive, negative. Cation's always first. What's the state of water? Liquid. It can't be aqueous because that would be water dissolved in water. This doesn't make any sense, right? When you need a state symbol like this and there's not anything else given, assume it's at room temperature. I assume that you know that water is a liquid at room temperature. And then I'm going to look at K plus and SO4, 2 minus, and put those together to make K2SO4. And then I should really go check and make sure that that's not a solid. If you look at the rules, potassium is in that first row that's soluble with no exceptions, so this is aqueous. Then I need to balance the equation. So now we've got hydrogens and oxygens all over the place, right? You have a question?
Yeah, how do you determine the state of something that's not as familiar as water?
If it's an ionic compound, you would only be asked, if it's, ionic compounds tend to have really high melting points. And so if it's a pure ionic compound, it'll be a solid at room temperature, always. If it's in a solution, we just learned how to use the rules to determine if it's a solid or if it's dissolved, aqueous. I would assume that you would know the elements on the periodic table, nitrogen, oxygen, fluorine, chlorine, and the noble gases that are all gases at room temperature. You should know that carbon dioxide is a gas. But beyond that, I don't think you'd actually need to predict anything.
So at room temperature, it would be kind of what it is on the periodic table?
If it's an element, yes, it would. Mm-hmm. So we need to balance this. There's hydrogens and oxygens all over the place. So I'm going to go to the potassium first. Here's 1 potassium and here's 2. So I'm going to put a 2 in front of KOH. So I've got 2 potassiums. And then the sulfate. Do you see how the sulfate stayed together? So I have 1 sulfate here and I have 1 sulfate there, so that's cool. So I've got potassium and sulfate. And then these 2 hydrogens and those 2 hydroxides are what came together to make the water here. So I need a 2 in front of the H2O. We could look at it this way. In this one, I'm going to get 2 hydrogen ions, right? 2 hydrogen ions. Here, I put the 2 here because of needing the potassiums to balance. So that's going to give me 2 potassiums and 2 hydroxides. Oops. Then over here, there's 2 potassiums and 1 sulfate. So what's happening is I have 2 hydrogen ions and 2 hydroxide ions combining. So I've got 2 of those and 2 of those. That's going to give me 2 water molecules. There's various ways to get that balanced. So to write the net ionic equation, well, we need at least a rough complete ionic equation, and that's actually what we have right here. It's not all fancy, but it's there. This is aqueous, that's aqueous, this is liquid. This shouldn't be separated into ions. So we're going to call that H2O, liquid, because that doesn't separate into ions. This is aqueous, this is ions. Now I see that I've got potassium ions on this side and potassium ions on that side. Those are spectators. And there's a sulfate ion here and a sulfate ion there. It's a spectator, just watching. What's left are hydrogen ions, hydroxide ions, and this water molecule. Well, there was a 2 there. Let's try to be consistent. Put a 2 here. So what's left after we got rid of the spectators? Hydrogen ion plus hydroxide ion makes water. Most neutralization reactions have that same net ionic equation. H plus OH minus gives H2O. I probably should have put state symbols in there. So this is the net ionic equation. This is a molecular equation. Any questions? Yes?
So does changing the amount of the atoms not count as, that still makes it unchanged? So it's a spectator?
Well, if the reaction is balanced, you're going to have the same number. Oops. There it is. That was scary. You're going to have the same number of potassium ions here and potassium ions there. They're not going to be part of the reaction.
So how do you know exactly what is part of the reaction? Like I know the hydrogen and hydroxide and water.
It's everything that's left after you cross off the spectators. So the spectators, potassium ion and potassium ion weren't changed. They're the same on both sides of the arrow, so I cross them off. And sulfate is present as a product and a reactant. Nothing happened to it, so I cross it off. What's left, not crossed off, is the 2 hydrogen ions, the 2 hydroxide ions, and the 2 water molecules. And I just got rid of the 2's because I didn't need them for this balanced equation down here. Any other questions? Gas evolution reactions. So this was like dropping the Alka-Seltzer tablet in water. It forms a gas, right? Or mixing sodium hydrogen carbonate, baking soda with acetic acid is another one. So some reactions form a gaseous product directly. This is an example. If you mix sulfuric acid with lithium sulfide, it'll generate hydrogen sulfide gas and lithium sulfate. Hydrogen sulfide gas smells like rotten eggs. It's horrendous, really bad. Other reactions form an intermediate product that is unstable and decomposes. And that's what happens when you mix hydrochloric acid with sodium hydrogen carbonate. You form carbonic acid and sodium chloride. Carbonic acid is unstable, and it decomposes into water and carbon dioxide. So you end up with water, carbon dioxide, and sodium chloride. So these are the types of gas evolution reactions that we're going to need to know about. The first one is where you have H2S form as a product. And we're going to predict the products again, by looking at the individual ions, swapping partners, and seeing what happens. If you swap partners and you end up with H2S, you need to remember that's a gas and write a G. The other three form intermediate products that are unstable. And these are the products that we need to remember. H2CO3, H2SO3, and NH4OH. So you just need to memorize these. So what happens when H2CO3 decomposes? How do you remember what the gas is that's formed? All of these decompose in the same way. They decompose by losing a water molecule. So this is going to decompose. A water molecule is going to separate. And so I'm going to take this formula and I'm going to get rid of that. So I got rid of the 2 hydrogens and I got rid of one of the oxygens. What's left? CO2. That's a gas. Do you see how I did that? Okay. So here's this formula, right? H2CO3. So that's an H, a C, an O, an O, an O. I just write the letters individually. So I want to remove H2O. So I'm going to get rid of 2 of the hydrogens and 1 of the oxygens. And what's left? A carbon and 2 oxygens. Carbon dioxide. Okay, you see it now?
Well, why'd you take the H2O and put it on the right side if you took it away?
Well, because this was here and it breaks into these 2 things.
As the reactant.
This is a reactant and these are the 2 products that form when it decomposes. It falls apart all by itself. It's not
And
stable.
you have to remember this, you said.
Yeah, you got to remember it.
All color under 5, 4.
These 3 here are the ones that will lose a water molecule, and this one is a gas.
Okay.
You take a water out of it. So let's do that with H2SO3, that's sulfurous acid. So if I take 2 H's and an O out of that formula, what's left? Sulfur dioxide, SO2. See, this one's so bad, is it?
Then why does it look so weird on the example?
Because, so what they're showing you here is 2HCl and K2SO3. And so you would take these apart and swap partners, and you'd end up with KCl, that's this guy over here, and when you put the H with the SO3, you'd get this. They're not showing the intermediate product, and I'm showing you how this falls apart, and that's where the H2O and the SO2 come from. Let's look at the ammonium hydroxide. I think there's an example after this. So if I remove 2 H's and an O from that formula, right? So there's an H, and I'll get rid of one of those. That means there's 3 left, and I get rid of the O. NH3. So, ammonia. So I took this H off, and there were 4 here. I took one of those, so there's 3 left. And I get rid of the O, so I have an N and 3 H's left, and that's ammonia. Also smells bad. SO2 smells bad too.
Can you give them the table to know which reactants decompose like that, or will we need to memorize them?
I will not give you this table. You should remember these guys and that one. This is a gas because these are unstable. They fall apart. They fall apart by losing a water molecule. Yes?
In general, if the reactants have like H2O in the product, will water always form?
Can you say that again?
If in general, if the products have like an H2O inside of it, will they always like decompose with water as the product?
Oh, that's a good question. So if it makes something that contains H2O, not necessarily, no. Because if you made H2SO4, you could pull an H2O out of that, but H2SO4 is not unstable. So, yeah, there's really nothing better than remember these guys. Now, could you pass the class without remembering these four things?
Yes.
Yes. Yes, you can. Could you get an A?
No.
Maybe, I don't know. You know, if you're going to be a science major, learn this, okay? The rest of you, at least you've heard about it. Hey, I'm practical. I understand. We can't all remember everything.
So this is how you want us to write it, right? Will you give us a question on the test?
Well, here, I'll show you. So here's the instructions when we're writing equations for gas evolution reactions. You start with a skeleton, and then you swap partners, and then you have to remember these guys, those three guys, and then balance the equation. So let's do one. So here's aqueous hydrobromic acid and aqueous potassium sulfite. So hydrobromic acid is a hydrogen ion, and bromide, you just need one of each based on their charges. Potassium is K+, sulfite, that's the light version of sulfate. So K2SO3 aqueous. So whenever you have to predict what the products are, try swapping partners. Okay, so we're going to swap partners. We got those two together. We got these two together. So I've got K plus MBr minus, and I've got H plus and SO3 2 minus. So when I put these two together, I get KBr. Solubility rules are going to tell you that that's soluble. And when I put these two together, I get H2SO3. And that's when part of your brain should say, oh, that's one of them. This is unstable. This is going to come apart into water and whatever's left after I take the water out of it. So I'm going to get rid of, that's eraser is way too big. So I'm going to get rid of one of these oxygens. So there's only two. And I'm going to get rid of the hydrogens. And they didn't disappear. It's just that those are H2O. H2O is a, that's not a very good L. H2O is a liquid. This is a gas. That's the thought process, and that's the process of going through the equation. That when you see H2SO3, H2CO3, or NH4OH, your brain should go, ding, gas evolution reaction, and you separate them. And you've got to balance the stupid thing. 2 potassiums, so you need a 2 over here. And that gave me 2 bromines, so I need a 2 over here. I've got, see now the sulfite fell apart. It didn't stay together, so I can't balance this as a unit. But here's 1 sulfur and 1 sulfur. 2 hydrogens, 1 plus 2 is 3 oxygens, and 3 oxygens, so it's balanced.
I mean, I see how you went straight to H2O, but
So when I put these two together, I get H2SO3. You see that, right? And then I need to recognize that this comes apart. So that comes apart into water, and what's left after I remove 2 hydrogens and an oxygen from this, right, which is SO2. So I'm going to erase this and write those two in instead. That's how I got there. Okay? Any other questions? My question is, where did the time go?